The next 2 days we're going to look at the modulus and see it in a variety of different sort of contexts, both in terms of equations, inequalities and functions, and look at it both algebraically and also graphically. So today I'm just going to look at the algebraic side of it, and I'm not going to spend too much time looking at the graphs at all. There are a couple of extra videos I might post up that sort of have graphs on the page, but just you can generally speaking ignore them, and we'll do the graphs tomorrow and put everything into context then. I just want to give you, in the first instance, if you're given an equation to solve or an inequality to solve which has a modulus in it, how to deal with that and solve that algebraically. The key idea of a modulus, and you've met it before, you've met it with the formula for an area of a triangle on a coordinate grid, and also for the perpendicular distance. You would have come across this sort of these two vertical signs, and it refers to the absolute value. And there's also a button on your calculator, the ABS button, that also does the same thing. And the idea behind this is whether whatever is inside those, they form like brackets, but whatever's inside those sort of vertical lines, you're just taking the positive version of it. Okay, so we're wanting the absolute value or the positive value. So if x is positive, then it's just going to be x. If x happens to be negative, then in a sense you're taking the negative of that negative, which, if you think about it, negative over negative is positive. What I've written there is sort of the formal definition. So as a result of this, you can understand and appreciate certain basics. So we have, first of all, we have the scenario where if x is a constant, so the a that you see here, that's basically meaning a constant. So if x, the modulus of x is equal to a constant, then x is either that constant value or it is the negative of that constant. So for example, if we said to ourselves that the modulus of x was 3, then we know that x is either 3 or it is minus 3. We can extend that also to sort of other functions as well. So let's just say, for sake of argument, rather than a constant, it might well be another function involving x's and so forth. Then the same idea basically holds. Likewise, if you have a modulus is equal to another modulus, then you can say the same thing. The thing inside the first modulus is equal to either the positive or the negative version of the other expression on the right hand side. And lastly, we have a situation where we can use the idea of squaring both sides to be able to deal with the modulus. So again, if you had the modulus of x being equal to 3, then we know that the square of it is equal to 9. Now that example is a little bit too simple actually, and I'll go through an example which is a little bit more complicated, but it shows the usefulness of this idea of squaring both sides. And finally, whilst we're making some definitions, it's worth noting that the modulus of x being less than a positive constant, then we can rewrite that in a sense as a double-ended inequality where you have the x is between the positive and negative versions of a. So let's say the modulus of x is less than 3, then x is going to be between 3 and minus 3. So let's go through a few examples. This one is 3x minus 2, the modulus of 3x minus 2 is equal to 4. So using the first rule from the previous page, we can say that either 3x minus 2 is equal to 4 or 3x minus 2 is equal to minus 4. At the end of the day, we don't know whether this is positive or negative, but its value, its size is 4, so it's either positive or negative 4. So we can solve each of these. So adding 2 to both sides and dividing by 3, I get x equal to 2. Or if I add 2 to this x to minus 4, and then divide by 3, I get minus 2/3. There are two solutions that fit this modulus sign. An alternative method would be to take the idea of squaring both sides. So if I were to square both sides and sort of multiply it out, equate it to naught, I end up with either 3x plus 2 equals naught, in which case x is going to equal minus 2/3, or I have x minus 2 equals naught, in which case x is equal to 2. So I get the same two solutions by squaring both sides, equating to naught, solving by either using the minus b formula or factorizing, and getting my two solutions. I would particularly recommend that second method of squaring both sides when you have an equation that has a modulus on both sides. When it has a modulus on both sides, the squaring process will tend to give you a better outcome. Without boring you about sort of examples and so forth, it's just, take my advice, it just works better for when you've got modulus on both sides. So we'll do that this here. So if I square both sides, and then obviously I expand out the brackets. And when you've gone through that whole process of expanding the brackets, collecting like terms, equaling to naught, factorizing, you will eventually get the solutions. In this case, it is 7/4, or x is minus 4. Now, just very quickly, I can take the second approach, whereby I would separately say 5x minus 3 is equal to both the positive version of 3x minus 11 and solve that, and separately I could do the same thing with 5x minus 3 being equal to minus 3x minus 7. And when I expand each of those out and solve them, I get the same two answers. Sorry, there's a slight mistake there. Hang on, it's minus 8, minus 4. Minus 11 plus 3 gives you minus 8. Halve that, you get minus 4. So either solve it twice, once the right-hand side, for the sake of argument, positive, and then take the negative version and solve each of those, or square both sides. Moving on to an inequality, there are a couple of different ways of doing this. Now, this particular inequality, it is the modulus is less than or equal to 7. So what I can do is I can take the approach as follows, where I create a double-ended inequality, where I say basically 2x minus 1 is between 7 and minus 7. Since it's less than 7, the modulus of it is less than, the size of it is less than 7. Its size is between 0 and 7. And therefore it must be between 0 and 7 and 0 and minus 7, so between minus 7 and 7. And when you have a double-ended inequality that's fairly simple like this, you can, I suppose it's a bit, to me it's a bit of a cheat, and it's open to potential problems if you don't treat it wisely. But you could just say to yourself, well, as long as I do the same thing to all three parts, then the inequality still holds. If I add 1 to both sides, and halve, I get a solution here where it's minus 3 is less than or equal to x, which is less than or equal to 4. The alternative method would be that you would take both sides and square them. So we'd get 4x squared minus 4x plus 1 is less than or equal to 49. And then solving this, so we'd get critical values of 4 and minus 3, and since the quadratic is less than or equal to 0, then it's below the y-axis, therefore my values are between minus 3 and 4. So we're using that method that you would have practiced last week, where you're dealing with a quadratic inequality. Now I will just quickly warn you about being too quick with the first method, especially if the inequality is pointing in the other direction. So let's say, for sake of argument, if you had, I don't know, I'm making this up, 3x plus 2 modulus of was greater than, let's say, I don't know, 7, then it doesn't work out quite as simply. And it's certainly, you just be warned. And finally, an inequality where you have a modulus on both sides, where there's sort of algebra on both sides. I would strongly recommend you take the approach of squaring both sides. We'd end up with critical values of 5/3 and 3. This is a quadratic that's less than 0, so we're talking about a situation where we're looking for the values between the two critical values. So our solution will be values of x between 5/3 and 3.